Hey guys, down here. Welcome to Mount Everest, the tallest peak in the world at just over 29,000 feet. I love climbing mountains, I love backpacking, I love hiking, and certainly summiting Mount Everest would be on my bucket list. But have you ever realized the higher you climb, the harder it is to breathe? In fact, there is so little oxygen at the top of Mount Everest, there are literally thousands and thousands of discarded oxygen tanks littering the top of the most beautiful place in the world, which is why there's efforts to clean up the summit of Mount Everest. Did you know the higher you climb, the lower the atmospheric pressure is in the air? And what that essentially does is lower the amount of available oxygen your body has to breathe. And that's why it's harder to climb at higher elevations. So let's consider the relationship between those two variables, elevation and oxygen. The higher you go, the less oxygen your body has to breathe, making it more difficult to keep climbing. This is known as an inverse variation or an inverse relationship. And that's the topic of today's study. So let's jump into a few examples after we summit Mount Everest. Before we jump into today's examples, let's remind ourselves what the general form of an inverse variation function looks like. So just like we had general forms of a direct variation, we have general forms of the inverse variation, where y is equal to k divided by x. That is, y varies inversely as x, or we see y equals k divided by x squared. That would be y varies inversely as x squared. Another way to say that is that y is inversely proportional to x, or y is inversely proportional to x squared. And keep in mind, the relationship between these two variables is just like our elevation and our oxygen. As one goes up, the other one goes down. Or in other words, as one increases, the other one decreases. We have a seesaw problem. Now, a seesaw follows the law of the lever. And the law of the lever is expressed as an inverse variation, d equals k divided by w, where d is the distance from the lever and w represents the weight of the person sitting on the seesaw. So we have some information here. Carrie's weight and the distance she is from the pivot point of the lever, and we have Madison's weight. So let's write our inverse variation equation, which has actually already been given to us. Now we're going to use our known relationship to find our constant of variation. So let's substitute in Carrie's weight and her distance and solve for k, our constant of variation. We need to multiply both sides by 34, and our constant of variation therefore will be 34 times 1.8, which our constant of variation therefore is 61.2. Now we can take that value for our constant of variation and substitute that back into our equation. So we'll rewrite it as distance equals 61.2 over w, and we'll use that inverse variation equation now to find the distance Madison needs to sit away from the lever in order to balance that seesaw. So 61.2 divided by 38, Madison's weight, is going to give us 1.61 meters. All right, let's move to our next example. Again, we read that y varies inversely as the square of x. So that should tell us enough information to set up a general form of our inverse variation equation. Y equals k over x squared. We are going to substitute some known values in for y and x to find the value of our constant k. So 47 equals k over 2 squared, which is 4. Multiply both sides by 4 to get your constant of variation. And this is going to give us 188 for the value of k. We'll substitute this back into our inverse variation equation to get y equals 188 over x squared. And now we can find the value of y when x is equal to 5. Squaring 5 gives us 25. 188 divided by 25 results in the value for y, which is, drum roll please, 7.52. All right, let's take a look at one more example here. We see that the number n of squares tiles it takes to cover a floor varies inversely. That should make sense. The larger your square tiles are, the fewer you'll need. So it says we have 140 squares that are 12 inches in length. It covers our square floor. So what's going to happen to the number of tiles we need as we reduce the size of the square down to 6 inches? So let's set up some variables. N will be the number of squares needed. L is the edge length, and we know that the number varies inversely as the edge length squared. So our inverse variation is N equals K over L squared. We'll substitute the values that we know into our inverse variation equation to find the value of K. So we have 140 equals K over 12 squared, which is 144. Multiply both sides by 144, and that's going to give us our value for K. So K now is going to be equal to 21,000, just kidding, 20,160. We'll substitute that back into our equation. Y equals 20,160 divided by the length edge squared. Now our new length edge, or our square tile, is now 6 inches in length. So we'll square 6. That gives us 36. Hi, buddy. You want to come in and say hi? Say hi to everybody. Are you going to be a mathlete someday? Yeah. All right. Say goodbye.
Bye.